Problem 1. A railgun is a device that can propel a projectile rapidly with a magnetic force. In the railgun shown, the driving voltage is 500 kilovolts, the projectile has a resistance of 20 ohms, a length of 20 centimeters, and a mass of 3 kilograms. The magnetic field has a strength of 10 Tesla, and the rails are very long. How fast is this projectile moving when it leaves the railgun? Please note that I have asked a similar question before, but that was before we started discussing induction. Please pause this video and attempt the problem. So what makes this question different than the last time I asked the railgun question is that I did not give you a length. I just said that the rails are very long. One way to interpret this is that the projectile will reach some sort of equilibrium state before it leaves the rails. Now, if there is a net magnetic force acting on this, the projectile will be speeding up, so it has not reached an equilibrium state. So what would be required in order to not have any force? Well, force is equal to B times I times L. So if there was no magnetic field, there would be no force. However, there is a magnetic field. If there was no length, there would be a force. However, there is a length. So we're left with the last one. If there is no current in this, then there would be no magnetic force. Now, when it starts from rest, it's being driven by this voltage source of 500 kilovolts. So what could happen is that once it's going fast enough, if it produces 500 kilovolts of electromotive force, that will oppose the 500 kilovolts from this and will cause a net zero current. So now to answer this, we need to ask how fast is it going in order to produce 500 kilovolts of EMF, or as it's often called, 500 kilovolts of back EMF, because it's opposing the driving voltage. So we assume that the EMF produced is equal to the voltage of the source. EMF is given by, or the magnitude of EMF rather, is given by d phi dt. And d phi dt, because we don't have any angles, we don't have any rotation, and the magnetic field is perpendicular to the plane that these rails are on, we can go ahead and ignore the sine theta component, and it's just phi is b times a. Since b is not changing, we're going to ignore that term and look solely at the term where a is changing. Now, area is equal to length times this distance. This length is not changing, so once again, we use the product rule and say that the rate of change of area is L times V. So EMF is equal to B times L times V. We know EMF is at 500 kilovolts. The L should be the length of this, which was 20 centimeters or 0.2 meters, and the magnetic field was 10 Tesla. So if we solve for velocity, we get it's equal to voltage divided by BL for a velocity of 2.5 times 10 to the 5th meters per second. Question 2. If we were to short out the battery in problem 1, what acceleration would the rail experience? And as a reminder, the projectile has a resistance of 20 ohms, a length of 20 centimeters, and a mass of 3 kilograms. The magnetic field has a strength of 10 Tesla, and we decided that the final speed of the projectile was 250,000 meters per second. Please pause the video and attempt the problem. So to solve this first problem, we assumed that this EMF would completely oppose this voltage source, and in doing so, there would be no more current. However, if we're shorting out this voltage source, then this is still producing EMF, which means that now we are able to drive the current. And furthermore, we could calculate this, but because of the way we solve problem 1, we know that the back EMF is going to be 500,000 volts, which leads to, with a 20 ohm resistance, that leads to 25,000 amps of induced current. We can use force is equal to BIL. B is, again, the 10 Tesla. I is the 25,000 amperes of current. And the L is the 0.2 meters, to say that there are 50,000 newtons of force acting on that projectile. Using Newton's second law, we can solve for acceleration. Acceleration is equal to net force divided by mass. And that gives us a whopping 16,670, or 667 if we want to round there, meters per second squared. Problem 3. In the following scenarios, what direction is the induced current? So for this, we will be using Lenz's law. And because of the nature of this question, I'm not going to do my usual, please pause the video. I just want you to think about it real quick in the time that I pause speaking. So the first question, magnetic field coming out of the page, field is getting stronger. What direction will the induced current be? Well, if the magnetic field is coming out of the page and it's getting stronger, it's changing so that it's getting more out of the page. We are getting more flux in this loop. So Lenz's law states that we will create a current that will oppose that, to create less current, or that makes a flux more out of the page. So to find the direction of current, here's an alternate version of the right-hand rule. Stick your thumb in the direction you want the magnetic field to be. In this case, that would be into the page. See which directions your fingers curl. From the perspective of the flux going into the page, our fingers are curling in the clockwise direction. B. The magnetic field is coming out of the page and the loop is getting bigger. So this time the magnetic field is keeping its same strength, but if the loop is getting bigger, then it is still able to put more flux into it. So the flux is becoming more out of the page. So once again, we are trying to create a flux that's into the page, or rather the induced current will try to create a flux into the page. So thumb pointed into the page, our fingers curl around in the clockwise direction. Question 3. The magnetic field is coming out of the page, loop is getting smaller. So again, the magnetic field is coming out of the page, but this time, since the loop is getting smaller, that means that there's going to be less flux in the loop. Less flux in the loop means that the induced current will try to create more flux in the loop that is coming out of the page. So this time, hold our thumb so it's coming out of the page, and see that this time our fingers curl in the counterclockwise direction, or anti-clockwise direction if you prefer. Question D. Magnetic field is going into the page, and the field is getting weaker. The magnetic field is going into the page, and the field is getting weaker. The field getting weaker means that the magnetic flux is decreasing. But the magnetic flux is decreasing in the direction into the page, which means we could say, or which means that the induced current will try to increase the flux into the page. So it will try to create a flux into the page. So to determine the direction of the current, point your thumb in the direction of into the page, look at your fingers, they curl once again in the clockwise direction.